All right. How do we determine the amount of heat in a chemical process or reaction? I want to state too, when I use the term chemical process, chemical reaction, they mean the same thing. So I may use them interchangeably. Most of the time in this semester, we're talking about chemical reactions, but I want to use chemical process as well so that you know that these words are used interchangeably, right? Because in some other applications, like if for those of you that want to go on to engineer, you may hear things like chemical process. Okay, so how do we determine the amount of heat, right? In the form of enthalpy. Enthalpy is what we've talked about. We've also talked about delta E, right? But how do we determine it? And there's two ways that we can determine the amount of heat transferred or that flows in a chemical process. One way is we can measure it experimentally through a technique called calorimetry. And the other way is we can calculate it, right, from other experimentally determined enthalpy changes. And this is based on something called Hess's law. So I want to talk about these two methods next. So starting with calorimetry. This is a experimental method we can use to measure the amount of heat flow. And the heat is exchanged with some calibrated object, which we actually refer to as the calorimeter. And we can measure the change in temperature, right, of the measuring part of the calorimeter. We can measure the change in temperature as a result of whatever our chemical reaction or process is. And this is then converted into the amount of heat transfer or heat flow. So this figure here, right, and this is similar to what you will be doing actually in, I think it's experiment number 3, which is setting up what's called a coffee cup calorimeter, right? You're going to use 2 styrofoam cups, and that is your calorimeter. In theory, right, your calorimeter doesn't allow heat to escape or come in from the outside surrounding environment, but that may not necessarily be the case, right, in our experiment. But in an ideal situation, right, theoretically, the heat is only exchanged between our system, whatever chemical reaction we're studying, which would be inside of our cup, and then the calorimeter, right, which in this case represents the 2 styrofoam cups. So let's talk about like the principles or the theory behind calorimetry. So let's say that I have some hot piece of metal, right? I take a piece of metal, I heat it up, and then I have cool water inside of a cup. If I place that hot metal in the cool water, heat will transfer from the metal to water. Heat will transfer from the metal to water. Now, based on this, right, what will happen to the temperature of the metal and the water? What will happen to the temperature of the metal and the water? And this may just, you may already know this, it may pop into your head. If not, I want you to pause this video and think about it for a few minutes. Don't look it up, right? If you do pause it, just intuitively, right, what will happen to the temperature of the metal and the water if heat is transferring from the metal to the water? So the temperature of the metal will decrease, right? Because it's losing heat, and the temperature of the water will increase as a result of receiving that heat from the metal. So that's what's shown here schematically, right? This vessel here is water, denoted by W, and then we have this heated up metal, which represents our system that's placed in the water. And this arrow with Q is basically denoting or showing that heat is escaping from the metal into the water. And we have this thermometer in here so that we can actually see the temperature change of the water as a result of this heat transfer between the metal and the water. So eventually, right, the heat from the metal will escape into the water until up into a point where thermal equilibrium will be reached, meaning that the temperature of the metal and the water will be the same, right? That is what thermal equilibrium means, that we've reached equilibrium. This is my notion of equilibrium using my hands, right? Where the metal and the water are at the same temperature. So the heat exchange is only between the metal and the water, because in a calorimeter, right, our system should be closed. So we shouldn't have heat escape or heat absorption from our outside surrounding environment. So the heat exchange, in theory, is only between the metal and the water. Because of that, the net change in heat is zero. And this is based on the first law of thermodynamics, because energy is conserved, right? Because we can't create it or destroy it, it's conserved, so that must mean the net change in heat is zero. So if we rearrange this equation, right? So this is heat Q of the metal plus heat Q of the water equals zero. And if we just rearrange it by bringing, let's say, the water over to the right, subtracting it from both sides, we basically see that the heat gained by the metal is equal to the heat lost by the water. The heat gained by the metal is equal to the heat lost by the water. The converse is also true, right? If the water was heated up and we had a metal that was cool, right? The heat lost by the metal would be equal to the heat gained by the water. So the heat of both substances, the metal and the water, are equal in magnitude but opposite in sign, right? Because we have a plus for whichever substance is gaining heat and a negative for whichever substance is losing heat, but the magnitude, the actual value of Q, is the same. So these are our principles. This is our theory for calorimetry that we are using when we actually measure the heat flow of some chemical reaction. So let's look at an example. So let's say we have a 120-gram block of copper and we heat it up to 100 degrees Celsius. Then we place it in our coffee cup calorimeter that contains 150 grams of water at 25 degrees Celsius. So what this looks like is we have the calorimeter set up, right? When we put the thermometer in our water, we see that the temperature, we've measured out 150 grams of water. And think about, how can we measure 150 grams of water? We're going to be doing that in the experiment, right? We place the thermometer in there and we see the reading is 25 degrees Celsius. Now we take this block of metal that we've weighed out, that's 120 grams, we've heated it to 100 degrees Celsius, then we add the copper into the coffee cup calorimeter. And once we do this, we see that our final temperature reads 30 degrees Celsius. So basically, once we reach thermal equilibrium, that temperature is 30 degrees Celsius. So we want to calculate the heat flow for the water and for the copper block. So if we just intuitively think about it, right, the copper block is at a higher temperature than the water. So the copper is going to be losing heat. Heat will be escaping from the copper into the water. And then our water will be receiving heat, right? Hence why we see that rise in temperature for thermal equilibrium. So to actually calculate this, first, we want to get the change in temperature of our water. So essentially, we're measuring heat flow. We're measuring the heat that leaves the copper, and we're also measuring the heat that is absorbed or received by the water. So first we want to measure, we're going to look at water first, part A. So the change in temperature of water is our final temperature, which is what I've written here, right? T for temperature, sub F, that means final temperature, minus initial temperature, which is the I for initial. That will give us the change in temperature. So our final temperature is 30 degrees Celsius. Our initial temperature of the water was 25 degrees Celsius. So our change in temperature of the water only is 5 degrees Celsius. It's 5 degrees Celsius. So next, to get the heat flow of water, we use Q equals MCAT. Go back and review. We'll also, I think we'll have some review problems and discussion this week around this as well, right? M is the mass, C is our specific heat, and we'll use specific heat of water. And delta T is change in temperature of water, because we're measuring the heat flow of water. So the mass of water was 150 grams. Our specific heat of water, this is a value that has been experimentally determined that we could look up, that would be given, is 4.18 joules per gram degree Celsius, times our change in temperature that we calculated, which is 5 degrees Celsius. So when we do this math, our heat flow, Q, is plus 3.1 times 10 to the third joules. It's positive, right? Because water is receiving heat from the metal. So that makes sense. Now let's look at the heat flow for the copper block. So same steps, we're going to get the temperature change of copper. So copper started out at an initial temperature of 100 degrees Celsius, and then it was cooled down to 30 degrees Celsius. So this is why our change in temperature is negative 70 degrees Celsius, right? Because we actually cooled down the temperature of the copper. Using Q equals MCAT, the heat flow of copper is the mass, which is 120 degrees. Not degrees, I'm sorry, 120 grams. This is the specific heat of copper. This is a value that would be given to you, times our change in temperature, which is negative 70 degrees Celsius. So here we have our heat flow for copper is negative 3.3 times 10 to the third joules, right? And it's negative because the heat is escaping the copper. It is losing heat. Now, when we compare the Q for, or heat flow for, both water and copper, you may notice that it's a little different from what I talked about in the principles earlier, right? Where I said the magnitude should be the same, but the signs will be different. So our signs are different to match the flow of heat. Our magnitude is somewhat similar, right? But it's not exact. It's not exact. So what does this tell you? Why do you think these values are not exact, even though theoretically they should be, based on the theory of calorimetry? Pause this video and think about it. This is my waiting for you to think about it dance. All right, welcome back. So the reason is because this was an experiment. right? If the reaction was perfect, then the magnitudes would be equal and we would just see a difference in the sign. So this tells us some heat flow was lost to the surroundings, which we would expect using styrofoam coffee cups, right? This is not a very well insulated calorimeter system. So we do have some heat loss to the surroundings. So an example, there are many examples of calorimeters, which I suggest you look at in the textbook. One example that I just want to highlight here is an instant cold pack, right? A cold pack that gets hot, or I'm sorry, gets cold because it's basic. You have a bag inside of water and then it's surrounded by solid ammonium nitrate. So when the bag of water is broken, the pack becomes cold because ammonium nitrate dissolving in water is an endothermic process. So it removes thermal energy, right? It absorbs energy from the water. And so it then becomes right cold so that it is able to remove thermal energy from your body. Isn't that cool? Like, just, and many of us may have used instant cold packs, right? But this is one practical example of a calorimeter. So we've talked about calorimetry, right? This is how we would measure it, measure the amount of heat involved in a chemical process. And next video, we're going to talk about how we would calculate it from experimentally determine enthalpy changes using Hess's law. See you in the next video.